operation. And so together, you get a one-time pad encrypted quantum state. So this is, say, for 1 qubit, you get a perfectly secure encryption, because if you don't know A and B, then this is going to be the fully mixed state. So somebody who just gets this state, he has no idea what it is. But if you know what A and B is, then you can simply undo, and by simply self-inverse operations, you can also apply X and Z according to these bits A and B and recover the original state sum. So this is what we call the one-time pad encryption. Because it looks like the classical one-time pad, except that you also randomize the phase. So that's kind of analogous to the classical one-time pad. That's the first ingredient that we're going to use, and the second ingredient is going to be classical homomorphic encryption. So we simply assume, kind of as a black box, that we have classical homomorphic encryption available. That also means that we make all the computational assumptions that you need to make in order to build classical homomorphic encryptions. But that also, these are the only assumptions that we're going to need, simply to allow to have classical homomorphic encryption. All right, so using these two ingredients, I'd like to show you this Clifford scheme. So it works as follows. If Dora here has the quantum state she would like to encrypt, what she can do is use the quantum one-time pad. So she picks two random bits, A and B. She encrypts this qubit using the quantum one-time pad, and she sends that to the evaluator, to Google. Now Google wants to, let's say, apply a Hadamard gate. So they could just simply go ahead and apply the Hadamard gate to this encrypted version of the state. So if they do that, what happens is something very subtle. So it's here, you see the encryption is A-B, and after applying the Hadamard gate, this will still be an encrypted qubit, but now the keys have switched to be A. This is simply because of the commutation relation of the Hadamard together with these polys. So the Hadamard is a Clifford gate, so it commutes nicely with poly operation. And if you do the math, you see that, so this is H applied to this encrypted qubit. If you kind of commute that through here, what happens is that these exponents here get switched. So you end up still with an encryption, but now the encryption key has kind of changed from AB to BA. So that means you cannot simply go on and just apply more gates, but somehow you'll get confused by how the keys have changed. But we overcome that using the classical homomorphic encryption scheme. So what you can do on top is you take your classical key, and now you use your classical homomorphic encryption scheme to encrypt that as well. So this is just a classical encryption of these two bits using the homomorphic encryption scheme, and that we send along as well, together with our quantum state, to the evaluator. Because now the evaluator does not just do the quantum part, but also use a classical update function, and in this case, if you apply a Hadamard, then you simply want to switch these two key bits. So this update function, it maps xy to yx. So it switches the keys inside this thing. So, and this you can do because it's a classically homomorphic encryption system. So you use the homomorphic property of the classical scheme in order to also update your keys. So now you have run the gate that changed the keys, but you have kind of changed the classical keys along with it accordingly. So then you're in good shape, because now you could just keep on doing other gates. So this example was for the Hadamard gate, but because the phase gate and also the CNOT are also Clifford gates, they have similar relations together with poly operations, so they kind of behave nicely together with the quantum one-time pad. So you can do this for the whole Clifford gates. So for all gates that are built upon these three basic gates. So that's nice. And of course you can then in the end send back, it still has this form that there's a one-time pad encryption, quantum one-time pad encryption, and a classical part. So how you're going to decrypt is simply you take your classical key, you decrypt that part, and that gives you the one-time pad key with which you can go and decrypt the quantum part. And then you recover your state, where now all the operations have been applied. So that's exactly what you wanted to achieve. So this is a homomorphic encryption scheme, but only for a limited set of gates. And the challenge is really to do a gate that is not inside the Clifford set. So the challenge in this case, for instance, is the T gate. So you've seen the Hadamard gate. What happens if you apply it to a one-time pad encrypted qubit is that it switches the two keys. So what if you do a T-gate and you also just apply the same strategy? You take an encryption, a one-time pad encrypted qubit, and you apply T to it. So it turns out that it depends what the encryption, what kind of the X part of the encryption is. If there was no X applied to the state, then you actually are fine by just applying the T-gate. However, if there was an X encryption applied in this one-time pad encryption, if you just do T on top of it, what you incur is an extra phase gate here. And so that's because the T is not in a Clifford gate, so they don't nicely behave together with the poly encryptions. You incur some extra error here. And that kind of puts you in trouble because you somehow, before you can continue doing other gates, you somehow have to remove this phase error here. So that's kind of the challenge. So how do we apply this correction, this inverse phase, if and only if some part of the encryption that we use has some particular form. In particular, whether there was an X encryption, that's determined by this A, whether there was one or not. So that's what we need to overcome. And that's the challenge. So here's a quick overview of the schemes that have been known so far, but I think in interest of time, I'm actually not going to go in details over this. I rather want to show you how we actually solve this problem. So yes, I can flash you the results, take all the pictures, and I guess the slides will be online anyway, so then you can look at it in peace. So these are kind of the trivial schemes. These are the schemes that were known so far, and here's our result. Our result it uses computational assumptions because we need to use classical homomorphic encryption. It is compact, so again, I think I don't have the time to explain in detail what it means, but it allows us to evaluate quantum circuits of polynomial size, with where well, you're going to see in the end what exactly the property is. So how do we solve this problem? How do we overcome the challenge? So in order to explain how it works, so like the way we solve the problem is by introducing such a gadget that helps you achieving exactly that task. A gadget is a quantum state that can be efficiently constructed and used. So you have to build it, you can use it efficiently. Efficiently is always polynomial in the security parameter, both in size and in the time it takes to use it. And it does exactly what we want, namely it applies a correction if and only if an error was present. So if and only if there was an encryption used that had A equals 1, well then it removes a phase. So that means if you had a 1 here, then we incurred this extra phase gate by just applying the T straightforwardly, and this gadget, once we put it through, then actually removes that phase gate in that case. And if there was a 0 here, so that means there was no X operation used when encrypting that state, then we don't need to do anything, and the same state that we put in also comes out on the other side. So that's kind of the magic gadget that does the trick. The question, of course, is how do we build that? And actually, this is going to be used up in the process. And in order to explain you how we build that, I need to take a little excursion with you into the wonderland of theoretical computer science. So in order to understand how we build the gadget, I need to introduce to you Barrington's theorem. So I don't know, who of you has heard of Barrington's theorem before? Yeah, 3. That's why all the rest of you, I'll take you on the long and winding way up to the theoretical computer science wonderland. So, in order to understand Barrington's theorem, you need to know what a permutation branching program is. So permutation branching program is a funny way to compute a Boolean function. Boolean function, say, has 2 inputs. They're both n-bit strings, x and y, and it has Boolean output, so it's a 0 and 1 as output. And how it works is the following. It consists of a list of instructions. Say this list here. Each instruction is kind of indexed by a bit of the input. So xi is a bit of the input, yj is also a bit of the input, xk is another bit of the input. And for every of this instruction, there's two possible permutations. So pi and sigma prime, sigma double prime, these are permutations on k elements. So they're simply permutations of the elements up 1 up to k. So they're elements of the symmetric group Sk. And what you need to do is the following, and so the output of such a permutation branching program is the product of all these permutations. And this output is guaranteed to be either the identity permutation on these k elements, or some fixed cycle permutation of these elements. So don't worry, there's going to be an example on the next slide. And we're going to say that if the output is the identity, so if the product of all these permutations is the identity, then the function output is actually 0. So the function output of f given on these inputs x and y is 0. And if it's this fixed cycle, then the output is 1. And there's going to be, we're going to have these terms of a length of the permutation branching program. This is simply the number of instructions here. And the width of the permutation branching program is k, so this is the size of the permutations. So this is kind of a funny way to compute functions, and here's an example. Let's compute the OR function with a permutation branching program. This permutation branching program is going to have length 4 and width 5, and here it is. That's the permutation branching program that computes the OR function. So let's verify this simply by going through all the possible inputs. So what you need to do is the following. So if you want to compute the OR of 0, 0, well then x1 is 0 and y1 is 0. That means you need to kind of first take the permutation that is indicated by this first instruction. So this was 0, so we take this upper permutation. So this is denoted here. This is some cycle notation saying that 1 is mapped to 2 and 2 is mapped to 3. So that's the permutation is going to look like that. And then you simply take the product or the concatenation of all these permutations. So if you follow the path, so here you always have to take the upper elements because the inputs are 0. So if you follow through the path, so you're going to see that the first kind of path ends up on the first one. So in overall, the product of all this is going to be the identity. And therefore, the function evaluates to 0, which it should be because the OR of 0 and 0 is 0. And so you can check all the other possibilities. So if you have 0, 1, then you have to take the 0 here, and then the 1 here, and then the 0 here, and the 1 here. And if you concatenate all those, you end up with some fixed permutation is different from the identity, and therefore the output is 1. And you can check that this is indeed the case, so then taking the identity, and then another one at the end. Or in the last case, well, here you have 3 times the identity and this last permutation. And so that's kind of a brute force verification that this permutation branching program with length 4 and width 5, it computes the OR function. So why the hell would that be useful? It's useful because of Barrington's theorem. So here it comes, and it's a slight variation of the original theorem. It says that if you have a function on 2 inputs, say of n and n bits, to Boolean function mapping to 0, 1, and if this function is simple, formally people say that it's in NC1, I'll explain in a second what that means, then there exists a permutation branching program for f, which has width 5, so constant width, and which is not too long, which the number of instructions, so the length is just polynomial in the input size. It's polynomial in n plus 2. So NC1, what is that? Well, don't bother too much. You can just simply think of it as simple functions, very simple functions. So in particular, actually, if P are the functions you can evaluate in polynomial time, and L are those you can evaluate in logarithmic space, then NC1 is even a subset of those. So it's very, very simple functions. And this is just some sad fact about computational complexity, that we can't prove anything, so there's no formal proof that NP, so even this big set, is actually different from NC1. But that's just because we don't know too much about computational complexity. But nevertheless, people think that all these classes are actually different, and so these the functions used here, they are just very simple functions. And fortunately for us, people work very hard in classical cryptography to put the decryption function of classical homomorphic encryption systems to make those as simple as possible. Because in order to get fully homomorphic encryption, you need to have a very simple decryption function. And in fact, like basically all of the recent constructions of fully homomorphic encryption, they make sure that the decryption functions are in NC1. And that's exactly what we need, because then we can apply Barrington's theorem, which gives us a permutation branching program for this decryption function. So let me show you how this now all comes together. Here is how we build our gadget. So on a high level, the idea is the following. We use the permutation branching functions for the decryption function of our classical homomorphic encryption system. Because that's what kind of, remember, we have to do something that depends on this A. It depends whether A is 0 or A is 1. But we only have an encryption of it. So we somehow need to decrypt it first, and then depending on what the result is, we either have to apply a quantum operation or not. So the input of the gadget is some quantum state. Then we use inside the gadget the permutation branching program, which exists due to Barrington's theorem of this function. It has two inputs. It has the secret key as an input, and it has this encryption of A as an input. And then what we're going to do is that we're going to apply the inverse phase gate on kind of like these paths, but only the ones that are not the identity. So if the path is not the identity, so that means that A is 1, then we're going to apply an inverse phase gate, and otherwise we don't. And after that, it's like a little trick, we do exactly the same permutation branching program in reverse. And this is to make sure that we know where the output is. So because we put the quantum input here on this branch, on this first kind of possible input, then actually you want to make sure that also the output comes out there. And how we do that is, well, we don't know through which of these 5 paths it will go, but if you just put the inverse of the same construction here, then we know, well, it's going to come back on that first piece as well. So we know where to look for the output. Things are a little bit more complicated than that. So in this case, it would be that the input goes in here and kind of follow that path. In this case, A would be 0, so it goes through that part of the path here where we don't apply anything, and then it comes back. Of course, now we somehow have to make this more concrete because the input is a quantum state. So what do we mean by this path? So the problem is that the input to this decryption function is somehow split into 2 parts. You know? The Dora, I have the secret key. She's the one who created all these keys. And the evaluator, Google, he's the one who has the encryption of A. Well, that sits on the other side. So somehow we have to split up these permutation branching programs into steps that are done on Dora's side and into steps that are done on Google's side. And so how are we going to do that? So here's an example. It's the following. So we're going to use, say, EPR pairs according to the permutations that are given by the permutation branching program on Dora's side. So she's going to simply prepare EPR pairs, and because by Barrington's theorem the width is 5, so it's just 5 EPR pairs per instruction, and overall so polynomial allowance. She's going to prepare these EPR pairs. So that's going to be part of the gadget, and then part of the instructions how to use the gadget. So when Google also wants to use it, what Google is going to do is going to do Bell measurements to connect up these EPR pairs. So you will recover the same structure as in the permutation branching programs by a combination of how the gadget is prepared and how the gadget is used. So the preparation only depends on the secret key, so that's Alice's input, and how it's used depends on what the encryption at the moment of this A is. This is how Google is going to use it. So overall, the quantum state is going to go through this maze of entanglement. Yeah? So it's basically just teleported through that gadget. And in the end, because we set it up that way, so this was just the first step, so here, it will be teleported through this gadget. So this is how the gadget is prepared. This is what Dora does. So she prepares all these EPR pairs. And then, if you want to use it, you Google, then you come in and connect your inputs here to the first EPR pair. You do all these bell measurements here in between. And then magically, because of the property how it is constructed, actually this phase gate is removed in case that A is 1. And it's not done anything here in case that A equals 0. So that's exactly what we want. So let me give you an overview of the whole scheme to give you a bit of time to digest. So key generation is consisting of a step where classical keys are generated. So this is a classical homomorphic encryption scheme here. So we have a public key, we have a secret key, and we have our evaluation key, classical. And then on top of that, we generate a bunch of gadgets, because we need one gadget per T gate that the evaluator is going to do in order to remove this phase gate. So we construct a fixed number of these gadgets. And then the encryption is basically just in the same as in the Clifford scheme. So we pick randomly 2 bits per qubit, apply the quantum one-time pad, and encrypt these classical bits with our homomorphic encryption scheme. And then that can be sent to the evaluator. The evaluator then, for the Clifford gates, it simply applies the Clifford gates directly. So that's the same thing as in the Clifford scheme. Plus, classically updates these keys through the homomorphic property of the classical scheme. And on top, when using the T gate, then it also just applies a T gate, but then we have to use one of the gadgets in order to remove this additional phase gate. And after that procedure, we're still back into this kind of the invariant of the scheme that we have a properly encrypted qubit under a quantum one-time pad together with classical information that tells us what the keys are. And so you can just go on and apply more of these gates. The only thing that you need is one gadget per T gate that you want to apply. And that's, well, and then decryption is the straightforward thing because it still has this form. So of course, what you're going to do is you're going to use your secret key to decrypt the classical key, and then you recover these 2 bits, and you use those to uncover the quantum state where now this unity array has been applied. Yeah, so in practice, everything is slightly more complicated than that because, of course, you somehow, when using these gadgets and you're teleporting your state through this maze of entanglement, you incur some extra poly corrections. And you have to keep track of that. So that's something that after using such a gadget, you also have to correct for all the poly errors that occurred on the way. And so you have to know all the outcomes of all the measurements. You have to know how exactly the gadget is prepared. And so again, you're using the homomorphic property of the classical scheme to cope with that. And also just the way the gadgets are constructed, you have to be careful as well, because you also have to kind of encrypt these EPR pairs. Because if somebody was able to just like look at the gadget and kind of see how they are connected, well, that would immediately give you information about the secret key. So you have to be careful. You also have to encrypt that. So there's on the side of the quantum part of the gadget that I described, there's also a whole bunch of classical information you need to know. But all of that is encrypted under the classical homomorphic scheme. And so that's why it is secure. Proof to the security of the scheme. All right. I think that's the end of my talk. Well, yeah, I should finish with some open questions. So, as I just mentioned, this is not quite fully homomorphic yet. It's so-called leveled fully homomorphic because we still need kind of a limit on how many T-gates we can apply beforehand. We need to generate these gadgets at the key generation phase. And you can only apply that many T-gates. And once you run out of these gadgets, well, you can ask the secret key creator for more. That works. But it's not really that he just can keep on going as long as he wants. Once he runs out of these gadgets, then that's it. And this is why it's called leveled homomorphic encryption. So in order to get fully homomorphic encryptions, one needs to apply some more tricks. And currently we don't know how to do that. One could look at a somehow verifiable version of this. Somehow can we force the evaluator to do the right thing? So far the evaluator has the freedom to apply whatever operation he likes. So ideally we want to put in some checks there as well. And maybe we can use these techniques to build some quantum obfuscation schemes, but I won't go into that. So I'd like to thank you very much. I'd like to thank all the sponsors. I'd like to thank all the people who invited me here, and I'd like to thank my co-authors. And here's a little advertisement. QSoft is currently hiring 2 principal investigators. Go to this website if you're interested to join us in Amsterdam. Thanks a lot.
Thank you very much. So the paper is now open for discussion.
It's really very.
Yeah, it works. It was working.
Okay.
Sorry. All right. So that's really very, very nice. How much work does the Dory have to do? Dora, that efficient. So how much work does she have to do exactly? Who prepares the sketches, for instance?
The Dora, yeah, the one who.
So how is it compact then? It depends on the size of the circuit.
That's right, but you do that beforehand. So the compactness is defined in terms of the complexity of the decryption function. So in that sense, it is kind of a cheat. So you basically do the hard work beforehand, but you don't know yet what the evaluation will be. So yeah, and also of course the evaluator is not forced to use that many TKs. So in that sense, you do leave all the freedom of what to do to the evaluator, but somehow the hard work is done by somebody. Yes, and that somebody is not the evaluator. So that's the big difference to classical homomorphic.
All right. And one very small technical point. It's not enough that it's either identity or some fixed permutation. For what you showed to work, it has to be the fixed permutation does less than 1-to-1.
That's right. So, but that's guaranteed by Barrington's theorem, by the proof, is that either it is the identity or some fixed other cycle, actually. So the way the proof is constructed,
yes, that's right.
You are guaranteed that it's either this or that. So in that sense, you're sure that you're not going through that first path if it's not the other.
Thank you.
Can I ask the next speaker to start setting up? Then one more question.
Since you show the scheme that you send both quantum encryption and the encryption of the key in classical encryption to Big Brother,
Yes.
does that mean this scheme is as secure as the classical encryption itself?
Yes. So what we do is kind of an information theoretic upgrade to the quantum world of the classical scheme. But we do require, I mean, the scheme is just as secure as the classical homomorphic encryption scheme. Because if that one is broken, then you know the keys and you can recover everything. So, yes.
Thank you.
We have one more question.
So I'm wondering,
Yes?
can you use this magic state injection for the scheme to implement the T-gate?